Yeah, are we live? Okay. So, in today's interview session, we're going to be discussing about interview questions on dimensionality reduction techniques. It's nothing but PCA. Okay. So the first question would be, so in today's interview session, we're going to be discussing about PCA topic questions. So the first question would be, imagine you have 1,000 input features and one target feature in a machine. In a machine learning problem, you have to select 100 most important features based on the relationship between input features and the target features. Do you think this is an example of dimensionality reduction? So this is the first question, and the answers are S, A, S, B, no. What would be the answer? Yeah, the answer would be A. This would be an example of dimensionality reduction. Okay, the answer would be A. We'll go for the next question. The next question is also true or false. So the next question states that it is not necessary to have a target variable for applying dimensional reduction algorithms. True or false? The question states that it's not necessary to have a target variable for applying, dimensional reduction algorithm. Is it true or false? Obviously, the options would be A true, B false. So the answer for this question is A. Yeah, it would be true. So it is not necessary to have a target variable for applying dimensionality reduction techniques and algorithms. Okay, so answer is true. It is possible. Okay, we'll go to the next question. So this is the next question. So the third question stated, I have four variables in the dataset such as A, B, C, D, and I have performed the following actions. Step 1. Using the above variables, I have created two or more variables. Namely, capital E is equal to capital A plus 3 into B, and F is equal to B plus 5 into C plus D. Step 2. Then using only the variable E and F, I have built a random forest model. Could the steps performed above represent a dimensionality reduction method? True or false? So Akil Ramakrishna Reddy Saikam. Okay, see. Yeah, it's A. Yeah, both steps represent dimensionality reduction. Okay, we'll go for the next question. So the fourth question would be, which of the following techniques would perform better for reducing dimensions of a data set? A. Removing columns which have too many missing values. B. Removing columns which have high variance in data. C. Removing columns with dissimilar data trends. And D. None of these. What would be the answer? Any guesses? A. Yeah. Akhiladitya, for third question, it is true. So Akhiladitya says for fourth question, it's A. Yes, the answer is A. Removing columns which have too many missing values would be a good option for reducing dimensions of a data set. Okay, so A would be the option for fourth question. We'll go to the next question. So the fifth question is a true or false question. So it says that dimensionality reduction algorithms are one of the possible ways to reduce the computation time required to build a model. Is it true or false? PCA techniques are used to reduce computation time to build a model. Is it true or false? Yeah, it's true. It's an easy question. Obviously, to save time, we use PCA. Okay, we'll go to the next question. Next question. So the next question, which is sixth question, which of the following algorithms cannot be used for reducing the dimensionality of a data? The options are A, t-SNE, B, PCA, C, LDA false, and D, none of the above, or none of these. Any guesses? Okay. Nobody seems to have chosen one answer. Okay. Uh, so the answer for the sixth question would be option D, which says none of these. No, all the three are used for can are used for reducing the dimensionality. Okay, okay. t-SNE. I think you can read about it. I have more questions to do. Okay. So D is our answer. None of these are all can be used for reducing the dimensionality. Now we'll go for the seventh question. So the seventh question is also true and false. PCA can be used for projecting and visualizing data in the lower dimension. Is it true or not? It's a very simple question. And the answer for the seventh question is here. It's possible. Yeah, it's true. The statement is true. PCA can be used for projecting and visualizing data in lower dimension. We'll go for the next one, which is of course eighth question. So the eighth question was the eighth question states that the most popularly used dimensionality reduction algorithms is PCA. Which of the following are true about PCA? And the conditions are one, PCA is an unsupervised method. Two, it searches for the directions that data have the largest variance. Three, maximum number of principal components less than um, or greater than equal to number of features. Four, all principal components are orthogonal to each other. So the options are A 1 and 2, B 1 and 3, C 2 and 3, D 1 to 3, E 1 to 4, and F all of the above. So what would be the option for the eighth question? Yes, you are right. Sam Wilber is all are correct. So the answer would be option F, all of the above. Above conditions are or statements are correct. We'll go for the next question. So the ninth question. So ninth question states that suppose we are using dimensional reduction as pre-processing technique. Instead of using all the features, we reduce the data to k dimensions with PCA and then use these PCA projections as our features. Which of the following statement is correct? A. Higher k means more regularization. B. Higher k means less regularization. C. Can't say. And D. One of the above. What would be the answer? A. Okay, the answer would be option B. Higher k means less regularization. That would be the answer. So, and the explanation for this would be higher k would lead to less smoothing, as we would be able to preserve more characteristics in data, hence less regularization. Okay, we'll go for the next question. The answer for ninth question would be B. So the tenth question would be in which of the following scenarios is t-SNE better to use than PCA for dimensional reduction while working on a local machine with minimal computational power? Option A, dataset with 1 million entries and 300 features. Option B, dataset with 1 lakh entries and 310 features. Option C, dataset with 10,000 entries and each feature. Option D, dataset with 10,000 entries and 200 features. What would be the option? Option B, dataset with 1 lakh entries. No, the option would be C. C is the answer. C would be the answer. Okay, yeah. C is the answer. And the explanation would this would be t-SNE has coordinated time and space complexity. Thus, it is a very heavy algorithm in terms of system resource utilization. So the answer would be option C. Okay, we'll go for the next question. So, which of the following, 11th question, which of the following statement is true for t-SNE cost function? Emmanuel D. Yeah, I already explained, no? For question number 10. TSA has a quadratic time and space complexity. Thus, it is a very heavy algorithm. So for condition 3, which is see dataset with 10,000 entries and 8 features, TSA TSNE is used. Okay, TSNE is preferred over PCA for you know dimensionality reduction. Okay, for the 11th question, which of the following statement is true for t-SNE cost function? Three options are given. A, it is asymmetric in nature. B, it is symmetric in nature. C, it is same as the cost function for SN. Maybe symmetry. Yeah, you're right. It's option B. It is symmetric in nature. T is SNE is asymmetric. Okay, so t-SNE is symmetric. So option B would be the answer. Okay. So we'll go for the next question. So this is another question. Imagine you are dealing with the text data. To represent the words you are using word embedded word to wake. In word embedding, you will end up with 1,000 dimensions. Now you want to reduce the dimensionality of this high dimensional data such that similar words should have a similar meaning in nearest neighbor space. In such case, which of the following algorithm are you most likely to choose from? A. t-SNE. B. PCA. C. LDA. D. None of these. Any answer? Okay. The answer would be A. You are right, Akhil. A is the answer. t-SNE stands for T distributed stochastic neighbor embedding, which consider the nearest neighbors for reducing the data. So the answer would be t-SNE, which would be very useful for the scenario in the question 12. Okay. So A would be the answer for this question. We'll go to the next question. Okay. So the next question is a true or false kind of thing. So, okay. t-SNE learns parametric mapping. Is it true or not? This is t-SNE algorithm learns non-parametric mapping. Is it true or not? It's a very easy question. The answer is A, it's true. It also learns it learns non-parametric mapping. You can use parametric mapping in t-SNE algorithm. Okay, we'll go to the next question. Which of the following statement is correct for t-SNE and PCA? Option A, t-SNE is linear whereas PCA is non-linear. Option B, t-SNE and PCA both are linear. Option C, t-SNE and PCA both are non-linear. Option D, t-SNE is non-linear whereas PCA is linear. So what is the answer for this? Yes, it's true, Akhil. For the 14th question, the answer would be D. t-SNE is a non-linear algorithm, whereas PCA is a linear algorithm. Okay, that is the answer. We'll go for the next question. So the next question, you can see it on the screen. In t-SNE algorithm, which of the following hyperparameters can be tuned? A. Number of dimension. B. Smooth measure of effective number of neighbors. C. Maximum number of iterations. D. All of the above. Yeah, option D is correct. Akhiladitya for the question number 14. So for the question number 15, the answer is D. All of the above. So all the options are correct. So answer for 15th is option D. We'll go to the next question. So going to the 16th question, of the following what is of the following statement is true about t-SNE in comparison to PCA? Option A, when the data is huge in size, t-SNE may fail to produce better results. B, t-SNE always produces better results regardless of the size of the data. C, PCA always performs better than t-SNE for smaller size data. And D, none of this. What would be the answer for the 16th question? No answer. So option A is the correct answer, which states that when the data is huge in size, t-SNE may fail to produce better results. For the 16th answer, option A is the correct answer. Okay, we'll go to the next question. Next one is a big question. You'll be given sufficient amount of time. So this is a question. 17th question. Xi and Xj are two distinct points in the higher dimension representation, whereas Yi and Yj are the representation of Xi and Xj in lower dimension. First condition, the similarity of data point Xi to data point Xj is a conditional probability Pj by I. Second, the similarity of data point Yi to data point Yj is a conditional probability Qj by I. Which of the following must be true for perfect representation of Xi and Xj in lower dimension space? Option A, P j by I is equal to 0 and q j by I is equal to 1. Option B, P j by I is less than q j by I. Option C, P j by I is equal to q j by I. Option D, P j by I is greater than q j by I. What would be the answer? Okay, obviously it's a very big question. Okay, I can see. So the answer would be C. P j by I is exactly equal to q j by I. And the explanation for this would be the conditional probabilities for similarity of 2 points must be equal because similarity between the points must remain unchanged in both higher and lower dimension for them to be perfect present representations. That is the explanation for this. Okay, we'll go to the next question. Yeah, you're right. You're right, Akhil. 17 question. The answer is option C, which is equally. So the next question, you can see the image. I have zoomed it. So which of the following is true about LDA? Option A, LDA aims to maximize the distance between class and minimize the class distance within. Option B, LDA aims to minimize both distance between class and distance within class. Option C, LDA aims to minimize the distance between class and maximize the distance within class. LDA aims to maximize both distance between class and distance within class. Option D. What would be the answer? A. Yes, you're right. LDA aims to maximize the distance between class and minimize the distance within class. Distance. Okay, within. Option A is the correct answer. Okay, we'll go to the next question. So the 19th question, in which of the following case LDA will fail? A. If discriminatory information is not in the mean but in the variance of the data. B. If the discriminatory information is in the mean but not in the variance of the data. C. If the discriminatory information is in the mean and variance of the data. D. None of these. What would be the answer for the 19th question? You can see the options on the screen. It would be option A. Option A is the right answer, which says if the discriminatory information is not in the mean but in the variance of the data. So LDA will fail in case of option A. Okay, we'll go for the next question. So you can see the next question on the screen. Question number 20. Which of the following comparisons are true about PCA and LDA? Condition 1, both LDA and PCA are linear transformation techniques. Condition 2, LDA is supervised whereas PCA is unsupervised. Condition 3, PCA statement, PCA maximizes the variance of the data, whereas LDA maximizes the separation between different classes. Option A, 1 and 2 are true. Option B, 2 and 3. Option C, 1 and 3. Option D, only 3. Option E, 1, 2, and 3. Which would be the answer for this question? Yeah, you're right. Akila, all are true. All the comparisons of the LDA and PCA in this question statements are true. Okay. We'll go for the next question. The answer would be E. Okay. We'll go for the next question. What will be, so the 21st question will be, what will happen when eigenvalues are roughly equal? What will happen if eigenvalues are roughly equal? A. PCA will perform outstandingly. B. PCA will perform badly. C. Can't say. And D. None of the above. What would be the answer for this question among the four options? Yeah, the option would be B. PCA will perform badly. So the solution for this is option B. And the explanation for this is when all eigenvectors are same, in such case, you won't be able to select the principal components because in that case, all principal components are equal. Okay? So the answer for option for question number 21 is B. PCA will perform badly. Okay, we'll go for the next question. Okay, this would be the last question. So we're nearly 4:45. Okay, it's a very easy question. Okay, question number 22 stated PCA works better if there is a linear structure in the data. If the data lies on a curved surface and not on a flat surface, if variables are scaled in the same unit. Option A 1 and 2, option B 2 and 3, option C 1 and 3, option D 1, 2 and 3. Which among the three are true? With the question number 22. So the answer would be C. Only 1 and 2 are 1 and 3 are true. So the second statement is wrong. So the answer would be C. C would be the answer for the question number 22. Okay, today it's done. We have covered 22 questions under in PCA topic. Okay, that's it. We're done now. Today, you can thank you for coming to the interview session. Okay.